Hi, George Diamond here again. Let me take my orange baseball hat off and we'll go ahead and begin the next video. There you go. I think we're ready to get started. Now today we're going to take a look at something called integration by substitution. Now in our textbook this is section 4.5. Right? We use the Larson text. But we're going to look at something called integration by substitution. It's a technique that we can use to take what looks to be a very difficult, complicated integral and simplify it to where it's really very simple to find the antiderivative or to integrate it. Now, integration by substitution is kind of a technique for integrating composite functions, which the integrand is a composite function. Now, if y'all, hopefully everybody remembers the chain rule, so just a little example here. If you remember the chain rule, if you take the derivative of a function like sine 5x plus 6. Now the derivative when you take the derivative using the chain rules, you take the derivative of the outside, you leave the inside by itself times the derivative of the inside. So if I'm going to take the derivative of sine 5x plus 6, now the derivative of 6 is 0. So the chain rule now, when you take the derivative of sine 5x, the derivative of sine is cosine. So the outside function would be the sine function. So the derivative of sine is cosine. You bring the 5x down times the derivative of the inside function, so times 5. So the derivative of sine 5x plus 6 is cosine 5x times 5, or 5 times cosine 5x. So this is our derivative. Now it stands to reason that if we take the derivative now and we find the antiderivative, so if we were to take this derivative here and integrate it, okay, we should get this right here. We should get sine 5x plus c. Right? So we wouldn't get 6, but plus c. So we can integrate this, but we get this. So what we're looking at today, or what we're going to be looking at, is a technique. It's kind of the chain rule in reverse, where we're kind of integrating, evaluating, or indefinite integrals that are composite functions, right? So the integrand would be a composite function. Now, what we're going to be using is something called the general power rule for integration. Now, the general power rule for integration says that if g of x is a differentiable function of x, and you've had a function, g of x to the n power times the derivative of g of x. Now, this technique works because what you'll see the typically within the same integrand, because you see a composite function where you'll have the derivative of part of that function in the same integrand. Right? So like if you look at this function right here, we got 5 cosine 5x. Well, the derivative of 5x is 5. So I can see the derivative of the inside part of that function within the integral here. So this is a problem that would definitely that we could definitely integrate using what's called substitution, using the substitution method. So what the general power rule says, if you integrate g of x to the n power times the derivative of g of x. So if you can see the derivative of part of that integrand in the same integral, so you can see the derivative in the same integral, as you integrate, we'll give you g of x to the n plus 1 power divided by n plus 1 plus your constant of integration. So once again, now these are indefinite integrals, so we have to remember to add plus c each time we find an indefinite integral. So what we do when we integrate by substitution is we're going to let g of x be u. So we're going to let u equal g of x, right? So this the inside part of the function, right? Now, if we were integrating 5 cosine 5x, 5x would be the inside part of the function. We would let u equal 5x. So basically what's inside are parentheses there, the inside part. We're going to let u equal the inside part of the function, and the integral now becomes u to the n du, and then we just use the normal power rule. So we u to the n plus 1 divided by n plus 1 plus our constant of integration. So what this technique is, it's a method or a technique by which we change the variable literally in the entire integral from an integral in terms of x to an integral in terms of u. So we actually change the variable. And we change the variable not only do we change the x's, but we also have to change dx also, right? So we're going to rewrite this in terms of that. Now, there's a couple different ways to teach this. Some teachers teach to actually watch for the actual derivative, and then you can substitute at different times within the integration process. Now I'll show you my technique, and you can see how you like it here as we find the integral of a couple functions. So let's take a couple of indefinite integrals. Then we're going to do several examples. These will go pretty quickly, so I'm going to run through just a bunch of examples. Hopefully by the time we get done, you have a pretty good idea as to how to find an indefinite integral using substitution. So let's see if we can evaluate a couple of indefinite integrals now. So let me erase this. Now once again, this is section 4.5. All right, so section 4.5. Now also let me mention this is video number 1. There's going to be a video number 2 also, so there'll be a second part to this, but this is video number 1. Right, so kind of keep that in mind. Right, so with our directions, let's see if we can find the indefinite integral. Let's run through a couple examples. We're going through a bunch of examples. We're going to run through these pretty quickly, so just kind of keep up with me as we're looking at these. Let's start off with our first integral here. So example number 1. So example number 1. Okay, let's see if we can find the indefinite integral of the integral. Let's see, we'll do x plus 2 raised to the 5th power dx. All right. Now, how do we find the antiderivative of this expression here? Now, this isn't just, if this were the integral, x to the 5th power dx, well, we would just, remember the power rule, we just add 1 to your exponent. This would give us x to the 6th power divided by 6 plus c. So this we can do very easily. Now, this is not just x to the 5th power. This is x plus 2 to the 5th power. Actually, there's a couple ways to do this. One way would be to expand x plus 2 to the 5th power. That would take a lot of work, but you could do it. You would get a big long polynomial, and then you can integrate each part. But now integrating by changing the variable is much easier. So what we're going to do is this. So we're going to rewrite this integral from an integral in terms of x to an integral in terms of u. Now the inside part of the function is the n plus 2. That's what's inside our parentheses here. Right? The outside part of the function is the exponent. Right? So what we're going to do is we're going to let u equal. Let's let u equal the inside part of our function, x plus 2. So we're going to start it off like this. Right? So to rewrite our integral from an integral in terms of x to an integral in terms of u, start off by letting what's inside our parentheses basically be equal to u. So u equals x plus 2. Now what we're going to do is take the derivative of this expression. On the left-hand side, the derivative of u would be 1 du, or just du equals. Now as you take the derivative of the right-hand side, the derivative of x is 1, and the derivative of 2 is 0. So on the right-hand side, as you take the derivative of x, I'm going to leave this is 1 dx. Right, so we take the derivative, so we set up our integrate, our substitution. We let u equal the quantity x plus 2 within our integral, and then you can take the derivative of this. The derivative of u with respect to u would be du, and the derivative of the right-hand side would be 1 dx, or we can just say that du equals dx. Because remember what we're going to do, when we rewrite this in terms of u, and we convert our integral from an integral in terms of x from an integral in terms of u, there's 2 substitutions. Okay, first let's get rid of the x plus 2 here by substituting u in. So it'll be u to the 5th power times. Now remember, dx is actually equal to du, so times du. Right, so this is what the integral becomes when we change the variable. So not only do you have to substitute in for the x plus 2, substitute u in for the x plus 2. The x plus 2 is the inside part of your function. You also have to substitute du for dx. So you have to rewrite the dx part in terms of u also. Now let's find the antiderivative now in terms of u now. So the antiderivative, we're going to add 1, this will be u to the 6th power divided by 6 plus c. Now this is our antiderivative in terms of u. Now the last thing we want to do, so after you integrate it, right, let's take the x plus 2, since this is equal to u, and let's substitute this back into our answer now. So once we get our answer in terms of u, let's see if we can convert it back into our answer in terms of x now. So our final answer becomes x plus 2 to the 6th power divided by 6 plus our constant of integration, and this is our answer now. But so you got to start off by rewriting the entire integral from an integral in terms of x to an integral in terms of u. The x plus 2 is the inside part of the function, so you're going to let that be equal to u. Take the derivative, and then you have to substitute in for dx. So we got to remove the dx also. We're going to rewrite that in terms of u. And since du is equal to dx, that was pretty simple. Let's try another one. And so we're just going to quickly run through several examples here. So several examples. Let me erase this. So we'll get this done. There we go. Now, number 2. That's example number 2. This time let's see if we can integrate, all right, so 2x times the quantity x squared plus 1. So x squared plus 1 to the 2nd power dx. All right. Now, one thing that we could do here, right, so you can see we got this x squared plus 1 to the 2nd power. We could actually expand this. This actually wouldn't be that difficult to expand and multiply together and then integrate, right? But it's actually pretty easy by integrating by substitution too. So as you look at this, as I look at this integral, inside my parentheses, in the inside part of my function, you got x squared plus 1. When you look at the inside part of your function, you notice that the derivative of x squared is 2x. Well, I can see 2x also in the integrand. So this is a problem that we can solve by substitution, So what we're going to do is we're going to let the inside part of our function, the x squared plus 1, let's set that be equal to u. So I'm going to just come over to the side. Let u equal x squared plus 1. Okay, that would be the inside part of our function. Now take the derivative. Now the derivative of u is du. The derivative of x squared is 2x times dx. Now the derivative of 1 is 1. Right? Now, since we have to eliminate the dx and the x squared plus 1, now what I like to do is divide both of these by 2x. So 1 divided by 2x, du is going to equal dx. Okay, so let's make our two substitutions now. So this will be the integral 2x times x squared plus 1 to the 2nd power now becomes u to the 2nd power times. Now, instead of dx, we're going to substitute 1 over 2x du in for dx. So 1 over 2x du in for dx. Now notice what happens. The 2x's cancel out. So as you multiply these, the 2x's cancel. And our integral now becomes u squared du. Now notice, what looked at first to be a very complicated, difficult problem, right? Very difficult integral. This is a composite function that now becomes a very easy, simple integration now. So as we find our antiderivative in terms of u, this will be u to the 3rd power over 3 plus c. Substituting back in for u gives us x squared plus 1 to the 3rd power divided by 3 plus our constant of integration now. So that's going to be our integration. All right. Now let's try another example. Let's say we're just running through a bunch of these examples. So just some practice. Erase this. All right. Let's try our next example. Let's try this one here. Let's try some trig function this time. Let's try so number 3. Let's try the integral. Let's see, let's do 5 cosine 5x. So cosine 5x dx. So let's see if we can integrate the problem that we started the video with when we took the derivative. So to begin with, as you look at your integral, the cosine would be the outside part of your function. 5x would be the inside part of our function. So also, I've noticed within this integral, the inside part of the function, the derivative of 5x is 5. So I can see, the derivative of the inside part of the function is part of my integrand here. So I'm going to let u equal 5x. So I'm taking the derivative of both sides. The derivative of u is du. The derivative of 5x is 5 dx. Now, next thing I'll do is divide both sides by 5. Divide by 5, that gives me 1/5 du equals dx. So as I make my substitution now, this will be the integral 5 cosine u. So let's substitute u in for 5x, since we let u equal 5x times. Now dx is 1/5 du. Now notice what happens here. The 5's are going to cancel out, so those cancel. My integral becomes cosine u du now. All right, so what was initially kind of a hard problem now is just a little cosine antiderivative. Antiderivative cosine is sine, so it'll be sine u plus c. Substituting u back in for 5x in for u gives us sine 5x plus our constant of integration now. So that's going to be our antiderivative of the sine. Now remember when we started the video, I think we were taking the derivative of sine 5x plus 6. So that worked pretty well. Let's try another example. And so we're just going to run through a bunch of these and go through them pretty quickly. So kind of follow me with the u substitution as we set these up. Okay. And let's see, problem number 4. Let's try this one. So number 4, once again, we're going to find the indefinite integral. Let's integrate. Okay, x times the quantity x squared plus 1 to the second power dx. All right. So to get started, now I'm going to let u equal this. As you look at our integral here, you've got the x squared plus 1 to the second power. The inside part of the function is the x squared plus 1. The outside part of the integral here would be the power. That would be the 2. So let's let u equal the inside part. So u equals x squared plus 1. Take the derivative of both sides. The derivative of u is du. The derivative of 2x of x squared is 2x dx. Now I want to solve for dx now. So this gives 1 over 2x du equals dx. Now let's substitute in now. We have x times. Now instead of x squared plus 1, this becomes just u squared times. And instead of dx, this becomes 1 over 2x du. Okay. Now let's simplify within our integral. Right? Now notice that you got x on the bottom of this fraction, and this x here are going to cancel out. Okay, also that leaves me with 1/2. I have 1/2 du now. I'm going to pull that 1/2 out front of my integral. Because 1/2 integral u squared du. Okay, now, what looked to be a very difficult integral, now it looks to be much easier to evaluate now. So as we try to find our antiderivative, just a matter of using the general power rule now. So this should be 1/2 times u to the third power over 3 plus our constant of integration. And this will simplify then as 1/6 u cubed plus c. So this will be our antiderivative in terms of u. Now the last thing we want to do, let's convert it back into an integral in terms of x. So substituting the x squared plus 1 back into our integral now, this becomes 1/6 times x squared plus 1 to the third power plus c. And there you go. So that's going to simplify that. Let's try another one. And we're just running through a bunch of examples. All right, so that was pretty easy. And let's try another one. Okay, let's see this time. Okay, let's try this integral right here. Let's try, so number 5, let's try another trig integral. So number 5, let's do the integral. We'll do cosine 7x plus 5. So cosine of quantity 7x plus 5 dx. Now, once again, you should recognize this as the integrand here is actually a composite function. Cosine is the outside part, the inside part is 7x plus 5. So what I'm going to do to start us off, let's let u equals 7x plus 5. Okay. So basically what's inside your parentheses, that would be the inside part of your integrand. Taking the derivative now, so we have du equals, the derivative of 7x is 7, so it'll be 7 dx, and 1/7 du is equal to dx. So once you take your derivative now, I want to solve for dx on the right-hand side, so divide both sides by 7. I get 1/7 du equals dx. Now we're ready to rewrite our integral now. So our integral becomes cosine u times, and instead of dx, this becomes 1/7 du. All right. Let's pull the 1/7 out front, and this becomes 1/7 integral cosine u du. All right. Okay, now we've got our integral all in terms of u. We've pulled the 1/7 out, so we've got the integral simplified. So that didn't take very much effort really to do that. So let's go and find our antiderivative. Now the antiderivative of cosine is sine, so we have 1/7 sine u plus c. And substituting back in for u, let's take the 7x plus 5 and substitute it back in. So 1/7 times sine of 7x plus 5 plus our constant of integration. So this will be our antiderivative now in terms of x. All right. Let's run through another one. So that's number 5. Okay, let's try another one here. Let's try a radical expression. So we've not done a radical yet, so let's try a radical expression. All right, so we set this one up. Erase this up here too. All right, so we set this up. This will be the integral. And so this is number 6. Okay, let's try the integral, the square root of 2x minus 1. 2x minus 1 dx. Right. You know, at first glance, you know, without u substitution, this integral would be almost impossible to find the antiderivative of. Right? So you have to, as you look at the integral, the outside part of the function is the radical, the inside part of the function is a 2x minus 1. Now I'm going to rewrite this as the integral 2x minus 1 to the 1/2 power dx. So remember, we want to see the exponent there. So we want to see the exponent. So to get started, the inside part of the function would be the 2x minus 1. The outside part of the function is the exponent. So let's let u equal the 2x minus 1. And taking the derivative of both sides now, the derivative of u is du. The derivative of 2x is 2 dx. Now next I'm going to solve for dx. This gives me 1/2 du equals dx now. All right. Now we're ready to rewrite our integral from an integral in terms of x to an integral in terms of u. So our integral now becomes, instead of 2x minus 1 to the 1/2, now we have u to the 1/2 power times, and instead of dx it'll be 1/2 du. So we'll substitute that in for dx. So this is my integral, and now it's just a matter of, now I need to pull that 1/2 out front. So this becomes 1/2 integral u to the 1/2 power du. Okay. Now, u to the 1/2 power, that's just a simple application of the, just a simple power rule. Add 1 to your exponent divided by the exponent plus 1. So this becomes 1/2 times u to the 3/2 power divided by 3/2 plus our constant of integration. And then as we simplify now, this becomes 1/2 times 2/3 u to the 3/2 power plus c. Okay? So now as you divide, when you divide by this fraction now, you want to invert and multiply. So flip that fraction over, and we're going to multiply it to the u to the 3/2 power. So u to the 3/2 divided by 3/2 gives you 2/3 u to the 3/2 power. So flip that fraction over and multiply. Now the 2's will cancel out here. And we end up with, was that 1/3 u to the 3/2 power plus c. Now, substituting back in for u now, so we've got our antiderivative now in terms of u. Okay, all we have to do now is substitute it, is rewrite it back in terms of x now. So this becomes 1/3. So 1/3 times 2x minus 1 to the 3/2 power plus our constant of integration. So this will be our final antiderivative now. Okay, let's try another example now. All right, so let's try another one. I said we're just quickly run through a bunch of examples here. That was a radical. Okay, let me erase this. Okay, let's try number 7. Let's try this. Let's try another radical problem. That one wasn't too bad. Let's try the integral x times the square root of 2x minus 1 dx. Okay, what if we had to, now this is almost like the problem we just did. We just did the integral square root of 2x minus 1. What if this is x times the square root of 2x minus 1 now? Okay. Now first I want to rewrite it. Okay, this will be our integral x times 2x minus 1 to the 1/2 power dx. Okay, so we're going to rewrite it. We don't want that radical, so we need to see the exponent. Now, I'm going to start it off the same way. As you look at your integral here, the inside part of the function is the 2x minus 1. The outside part is the exponent here. So let's let u equal 2x minus 1. Du is equal to 2 dx, and 1/2 du is equal to dx. Now notice what happens now when we make our substitution. our integral becomes x times u to the 1/2 power times 1/2 du. Okay, now we got a problem. Okay, after we substituted in for our radical here, we have u to the 1/2. We remove the dx by rewriting it in terms of du. Now we have 1/2 du. Now notice now, in our substitution here, there is no x variable to remove the other x variable. That's still in our integral. Now remember now, you got to rewrite the entire integral in terms of x. In other words, you can't have the integral in terms of x and u. Right? It has to be one or the other. So we have to get this integral in terms of u if it can be evaluated, or if we can find the antiderivative using this particular method. Now, so right now there is no x variable from our substitution that will cancel out with this x here. But now sometimes, not always, sometimes we can go back to the original substitution. And we can use the original substitution to remove this other x variable here. So what we're going to do, let's bring this down here. And let's take the u equals 2x minus 1. And let's see if we can solve this for x. Okay, let's see if we can solve the original substitution in terms of x. All right? Add 1 to both sides gives us u plus 1 equals 2x. Divide by 2 gives us u plus 1 divided by 2 equals x. Now, x is equal to, now if you can solve for x and get a nice clean substitution here, x is equal to u plus 1 divided by 2, so I should be able to take u plus 1 over 2 and substitute it in for x in my integral now. So that's what I'm going to do. So instead of x, let's take the u plus 1 and let's rewrite this now. So this becomes u plus 1 over 2 times u to the 1/2 power times 1/2 du. All right. Now, that substitution now, that eliminated this x variable. Without that relationship there, I would not have been able to evaluate this indefinite integral. All right, so we would not have been able to find the antiderivative here. So let's see now. We're going to have to simplify this a little bit. Now, first of all, I see 2. I see the 1/2 and the 2 here. So I'm going to pull the 2 1/2s off. Right? So that ends up with 1/4 integral u plus 1 times u to the 1/2 du. So the 1/2 and the 1/2 here we can pull out in front of the integral. Now let's multiply the u to the 1/2 inside our parentheses. So we're going to use our distributive property here, looks like, to multiply back inside our parentheses. And this becomes 1/4 integral. This u to the first power, 1 plus 1/2 gives us u to the 3/2 plus u to the 1/2 times 1 gives us u to the 1/2 power du. Okay, all right, finally, I think we've got our integral simplified now. It's all in terms of u. Okay, now we're ready to find our antiderivative now. So I want to come over here, I want to erase a little bit here, let me get rid of this. All right, so let's bring this answer up here now. Okay, and let's go ahead and find our antiderivative. Now the antiderivative of u to the 3/2 power, and this becomes 1/4 times u to the 5/2 divided by 5/2 plus, now the antiderivative of u to the 1/2 power becomes u to the 3/2 power divided by 3/2. Okay, plus our constant of integration. So hopefully you can read this okay. This is the 3/2 power. And this is in a 5/2 power. Now, let's invert both of those fractions. Now, once again, we're just rewriting this as be 1/4 times. This will be 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus our constant of integration. Now, last, we want to multiply 1/4 inside our parentheses to both of those terms now. Now, as you multiply to this first term, the 2 will cancel out. That'll reduce to 2, so it'll be 1/10 u to the 5/2 power plus, multiply to this fraction here, that'll reduce to 1, that'll reduce to 2, and that gives us 1/6 u to the 3/2 power plus c. Okay, now we're almost done. The last thing we want to do is rewrite So we have our definite integral, or indefinite integral rather, written in terms of u. Let's convert this back in terms of x. So let's substitute the 2x minus 1 back in for u. And we have 1/10 times 2x minus 1 to the 5/2 power plus 1/6 times 2x minus 1 to the 3/2 power plus c. All right, this is a good example because remember now, whenever you attempt to substitute in and convert your integral from an integral in terms of x into an integral in terms of u, if you still have an x variable left that you can't cancel out by substituting in, and what you'll need to do is go and take your original substitution. If it's a simple thing to do, you can rearrange it to where you can remove that other x variable or that other variable, and then rewrite that in terms of u. Well, now we will try a couple more. All right, so this is a pretty good one. So erase this. There we go. All right, here we go. I'm going to get it down here. That's just be patient. There we go. All right. Okay, let's see. Let's try. Let's try this problem right here. Let's try another trig problem. This is pretty good. So number 8. Okay, let's try the integral 1 over cosine 2x dx. Let's try this right here. Now, first of all, I know 1 over cosine is secant. So let's see if we can rewrite this. Actually, I believe this should be cosine squared. So cosine squared 2x equals, there we go. So 1 over cosine squared 2x dx. Now let's rewrite this. This will be equivalent to the integral of secant squared 2x dx now. That's where we write this. Okay, now I know the antiderivative of secant squared is tangent, but now this is secant squared 2x. Now this is a composite function. So our integrand is a composite function. You've got the 2x here. 2x would be the inside part of your function. The secant squared would be the outside part of your function. So we're going to have to use u substitution to find our indefinite integral here. So let's let u equal 2x, and that means du is equal to 2 dx. 1/2 du is equal to dx. So we're ready for our substitution. Now let's rewrite our integral now from an integral in terms of x to an integral in terms of u. This becomes secant squared u times 1/2 du. All right. Excuse me. Okay. Now let's pull the 1/2 out front. This becomes 1/2 integral secant squared u du. All right. Now the antiderivative of secant squared is tangent, so this becomes 1/2 tangent u plus c. Okay. Now we have our antiderivative now in terms of u. Let's rewrite it back in terms of x. So this becomes 1/2 tangent to x plus our constant of integration, and that's our indefinite integral. Okay, let's try another. And I think we've got a couple, just 2 or 3 more examples, and we'll finish up. All right, so here we go. And let's see, let's try another trig problem. This will be problem number 9. So another trig, we'll try the antiderivative of secant squared, or sine squared 3x. Yeah, so we'll do sine squared 3x. Times cosine 3x, quantity 3x dx. Okay, now first you're going to notice now, sine squared 3x, this is the same thing as the integral sine quantity 3x squared cosine 3x dx. So, sine squared 3x is equivalent to this right here. That's the entire sine. Sine 3x is all squared, all right? So as we get started now, we've got this sine 3x to the second power here. Right? So I can see sine 3x would be the inside part of my function. The 2 here would be the outside part of my function. Also, I noticed that the derivative of sine is cosine. So, you can see, the derivative right there within the derivative of one part of the integral right there in the integrand with the other part. So the derivative of sine is cosine. So this is a problem that we can probably use U substitution to simplify. Now what I'm going to do, now we got, let's see, I'm going to start off, let's let sine, let's see, we'll do the inside part here, sine 3x, let's set that equal to U. We'll do U equals sine quantity 3x. All right, so we'll try this right here. As you take the derivative, du is going to equal, now as you take the derivative of sine 3x now, sine 3x itself is a composite function. So when you take the derivative of this function right here, you have to use the chain rule. Now, so you got to use the chain rule. Sine would be the outside part of the function, 3x would be the inside part of the function. So this would be, now the derivative of sine is cosine, bring the 3x down, times the derivative of 3x, which is 3. So this is the derivative times dx. So we have du equals 3 cosine quantity 3x dx now. Okay. Now I'm going to divide both sides here by 3 cosine 3x. Let's divide this side over here by 3 cosine 3x. Right, and we have 1 over 3 cosine 3x du equals dx. All right, so we're ready to rewrite this integral now to an integral in terms of u. All right, so this becomes, so sine 3x to the second power becomes u to the second power now times cosine 3x times, now let's replace the dx now. So the dx will be 1 over 3 cosine quantity 3x dx. So we have to erase this part right here just like, there we go. Now, so we made our substitution. Now notice now as you substitute in, these are here are going to cancel out. Now we still have the 1/3 though, so the 1 over 3 is still there, so let's pull the 1/3 out in front of the integral. All right, so the 1 over 3, we're going to pull that out front, and that gives us u squared. So 1 squared, this will actually be du, I'm sorry, not dx, so this will be du. All right, so du, so it'll be 1/3, we pull the 1/3 out, and this will be times du. All right, so what looked like a very intimidating problem at the beginning, has sine and cosine right there in the same problem. Okay, using U substitution, now look at the problem. So it's a much, much easier problem to deal with and to work with if we're trying to find our indefinite integral. So as you find our indefinite integral here, now this will be 1/3 u to the third power over 3, okay, plus our cost of integration, and this becomes 1/9 u to the third plus c, which is 1/9 times, let's see, u to the third, so this would be sine 3x to the third power plus c. So our final antiderivative is 1/3 sine 3x quantity sine 3x to the third power plus c now. All right, and we'll do 2 more problems. So 2 more. Let's try another radical expression. So another radical. So let's try another radical here. Erase this. There we go. And let's see, this time, okay, this is problem number 10. This is example number 10. Let's do the integral 3x squared times the square root of x squared minus 2. So x squared minus 2 dx. Okay. Now, first of all, let's rewrite this. So this will be the integral 3x squared times x squared minus 2 to the 1/2 power, okay, dx. Now, right away, I can see the inside part of the function is the x squared minus 2. The outside part of the integrand here would be the 1/2. So let's let u equal x squared minus 2. So we'll start it off with our u substitution. Take the derivative of both sides of our equal sign now. So the derivative of u is du. That'll equal. The derivative of x squared is 2x dx. The derivative of -2 is 0. All right, now solving this for dx, divide by 2x, divide by 2x here. That gives me 1 over 2x du equals dx. Okay, Now, let's go ahead and rewrite this now in terms of x. This will be the integral 3x squared. Instead of x squared minus 2 to the 1/2, this becomes u to the 1/2 now. Instead of dx, we have 1 over 2x du. Let's see, wait just a moment. I think we made a little I rewrote this. This is actually supposed to be 3x to the 3rd power. So this is actually to the 3rd power. It's pretty bad. I can't read my own writing sometimes, I think. All right, so as we integrate, this will be x to the 3rd power here. And actually, this is actually x to the 3rd. Just double check. Actually, it's x to the 2nd here. I'm sorry. This will be x to the 2nd. X to the 2nd. This is x to the 3rd power here. Okay, minus 2. And let me erase this right here. Let me just make sure I'm getting it right here, because I wrote the problem down in my own handwriting, and I really didn't write it down correctly. So let me try it again. And this becomes du equals 3x squared minus times dx. You take your derivative of both sides, dx. This becomes 1 over 3x squared du, and that'll equal dx. So as we make our integration now, this is 3x squared. It becomes u to the 1/2. And on the bottom of our fraction now, this becomes 3x squared du. And now the 3x squareds will both cancel out. Okay, this is what has to happen, because I do know that this integral, does have an antiderivative. So as we simplify now, this becomes u to the 1/2 du. Right, so once again, what looked like an intimidating antiderivative, an intimidating integral at the beginning, is now very, very simple. So once you change the variable, all it is now is u to the 1/2 power. If we find our antiderivative, this will be u to the 3/2 power plus over 3/2. Okay, plus c. This becomes 2/3 u to the 3/2 plus c. And as we rewrite our answer now back in terms of x, so substitute back in for u, this becomes x cubed minus 2 to the 3/2 power plus c. So our antiderivative, that's it. Okay, now I want to do one more problem. Let's try a fraction. So a problem that looks like a fraction. So let me try this one. So let's try a fraction. We haven't done a fraction yet. We've done several trig antiderivatives. We've done several radical antiderivatives. Okay, let's try this one here. This will be number 11. So 11 examples. This is a pretty good bunch of examples. Okay, let's try the integral -4 over x. So negative 4x over 1 minus 2x squared squared. So 1 minus 2x squared to the 2nd power dx. So let's try this right here. All right. Now to get started, first thing I notice, you have the parentheses here, 1 minus 2x squared raised to the 2nd power. This is the inside part of our function, so I can probably start off and say u equal 1 minus 2x squared. All right, so that should be, as we get started now rewriting this in terms of u. Okay, let's take the antiderivative now. The antiderivative of u is du, that'll equal. Now the derivative of 1 is 0, the derivative of negative 2x squared would be negative 4x. So negative 4x times dx. And solving for dx gives us 1 over negative 4x du. That will equal dx now. Okay. Okay, now we're ready for to rewrite our integral now. So as we substitute in, this is negative 4x over. Now on the bottom of our integral now, this becomes u squared times. Instead of dx, now this will be 1 over negative 4x du. Now the negative 4x's are going to cancel. And our integral now becomes, that's still the bottom of that fraction, this will be 1 over u squared du. And I can rewrite this now as the integral u to the negative 2 du. So 1 over u squared is the same thing as u to the negative 2. So again, we need to see that exponent there. Okay, let's use the power rule now. So this becomes u to the, we're going to add 1 to your exponents, so it'll be u to the negative 1 divided by negative 1 plus c. And this becomes, now as we simplify our answer now, becomes negative 1 over u plus c. All right, so negative 1 over u plus c. Now substituting back in for u now, becomes negative 1 over 1 minus 2x squared plus our constant of integration. And that's going to be our final problem. So hopefully we did 11 examples. Hopefully these examples will give you a good idea how to take what looks to be a very complicated, difficult problem, change the variable, right, and rewrite it so that it's actually a very, very simple problem, right? Some integrals you simply have to integrate them by use substitution. If we have any students that are in a high school, maybe taking AP Calculus, on the AP Calculus exam, they're going to make sure that you can integrate using use substitution. All right, so you see those types of problems all the time, and they're going to expect you to be able to use substitution to find an antiderivative. Okay, so hopefully you found some of these examples helpful.